Okay, how we doing, guys? This is for the college physics class, and this is my lesson on an introduction to electromagnetism. If you look on the school website, this is Unit 8, Lesson 2. Key concepts for this particular lesson are determining magnetic field strength and using the right hand rules as we explore electromagnetism. Okay, so here we go. All right, electromagnetism. We have defined magnetism as the interaction or the force that results from the motion of any charged particle. Okay, could be electrons, could be protons, could be ions for that matter. Any uniform motion or regular motion of charged particles will create magnetism. Interestingly enough, in order to get that to happen, you've got to have an electric field. So an electric field will cause the the charged particles to move in some fashion, and they create magnetism. Conversely, if you have a magnetic field, it's going to interact with the magnetism of the charge simply because charge will be spinning. It's what we call magnetic spin. And that could create motion. Therefore, it's going to displace the charge and create an electric field. That's why this is known as electromagnetism. It's the two forces unified. Okay. Now, a little bit of history. 1700s, amazing things were going on with electricity. Okay, late 1750s, our own Benjamin Franklin here in the United States finally convinces everybody that lightning is just a big spark, and that the same things that are causing the small sparks that people like Antoine Lavoisier were using, people over in Europe were they were using electricity left and right, but they were rubbing things. They were generally rubbing silk on glass, and producing electric charge and electric sparks and getting electrical responses from them. Um, and so they were using electricity. Ben Franklin actually tried to have a whole party where everything was started with electricity. Used a Leyden jar and blew himself across the room when he tried to start the fire in the fireplace using the electric charge stored in that Leyden jar. Okay. Um, this was what was being explored. And so this was the age of enlightenment. And so scientists became the rock stars of the time. And one of those European scientists who was very good at presenting stuff about electricity was a Danish scientist by the name of Hans Christian Ørsted. And he was doing an electricity demonstration. He was showing the new voltaic pile that was invented, or galvanic pile, actually, they were called then, because Alessandro Volta had discovered how to electrochemically produce electric current through chemical reactions, dissimilar metals, sandwich. We all talked about that back in circuits. Okay, so Alessandro Volta proposed that, and here we are. We're doing all these experiments about it, and this is the early and uh, um, okay, sorry about that. I was stuttering. Early 1800s, uh, Orsted is doing his demonstrations in front of audiences, and one of those demonstrations had a setup similar to kind of what I've got going here, except his wire kept going and went around. And someone had left a compass on his lab bench. And he noticed that every time he turned on his electricity, the compass would deflect away from where it would normally point. And so he went back to his lab in Denmark and he did more experiments. And he noticed that every time there was an electric current, it was producing and magnetic interaction with the compass nearby. And so he proposed that there had to be some sort of connection between the flow of electricity through a wire. Remember, they didn't know about electrons yet. So it was simply the flow of the electrical fluid um, through the wire is producing a magnetic effect which interacts with the compass, deflecting it from the Earth's own magnetism. English scientist by the name of Michael Faraday begins investigating this along with Humphrey Davies and several others at the Royal Society. Um, Others in Europe were doing it, and it was eventually Michael Faraday that defined what was going on here. And this is where we get what today we call field theory, because this was how he visualized what was going on with this. So if you look at my setup here, all right, I've got a wire and I've got a piece of cardboard here. And what he did was he had his wire. Imagine this going through my table here. I don't actually want to use electricity because I can't run enough current through this to produce a strong enough magnetic field that it's going to interact with what I'm working on. So give me a moment. Okay, so here's what he did. He had his wire here and he knew which way current was going to flow through it. And he says, okay, if I take a compass and I put it next to the wire, now imagine this happening. I'm not running a current through this, so the compass here is not going to deflect, all right, other than through my motion. But what he would notice is, notice how the compass is pointing in a specific direction right at the moment. For me, the compass is kind of going that way. If you look at it, let me bring it over here closer. You can see that it's going kind of off in this direction. This is the Earth's magnetic field interacting with the compass. He would turn on the electricity and the compass would then change. And then as he brought it closer, he noticed that the interaction got stronger and it would always change so that no matter where he was around the wire, the compass would point perpendicular to the wire and it would follow that direction. And so this is the conclusive proof that there was an interaction between the electricity in the wire and the magnetism of the compass. Therefore, they began calling this electromagnetism. Okay? So, electromagnetism happens because of the movement of charge. Well, if we force charge to move with an electric current, then that means that we're going to get magnetism from it. Okay? So, notes page for you, all right, about this. First off, the direction of current and the direction of the magnetic field are mutually perpendicular to each other. They're always perpendicular. Okay? So we have to be able to picture that on two-dimensional surfaces, namely our papers that we're writing on. But how do we do that and indicate three dimensions? We've got X, we've got Y, and now we need Z. So how are we going to do that? Give me a moment. Okay, if you recall, I did something like this way back when we did uh, circular motion, and I had to draw the picture of the car going into the board and the force acting perpendicular to it. And so this is another situation where I need to have an X direction, okay? So that's left and right. I need to have a Y direction for our purposes. Y is always going to be defined as toward the top of the page or up, and down toward the bottom of the page. And then our Z direction is going to be into or out of the board, into or out of the page. Okay? So, what we use to symbolize out of is a circled dot. And if you recall, remember that vectors are represented by arrows. And so, an arrow flying towards you, what part is closest towards you? The point of the arrow. And so that's the point of the arrow coming out of the board towards you. All right. This would be the feathers of the arrow flying away from you or going into this board. All right. So here we go. These are the symbols that we're going to use to represent vectors in 3 dimensions. And we need that now to talk about electromagnetism and the relationship between the magnetic field created by an electric current moving through a wire. Okay. Now, if you haven't already downloaded it, make sure you go to my webpage and download the right-hand rules worksheet for this, okay? We have to use the right-hand rules to represent our diagrams here, okay? So imagine this is our wire, the black part of the drawing here, okay? And imagine that we have a positive side over there, negative side over there, so the current is flowing from this positive over to the negative. That is the direction of conventional current flow. We're not actually worrying about the actual direction of electrons in the wire. We're worrying about what we call conventional current, which is the flow of positive charge. Now, if I were to try and put compasses all around this wire as the current is flowing, what I would notice is compasses down on the bottom over here would always point into the board compared to the wire. Notice that that's perpendicular to the motion of the current. On the top, those compasses would all point out. So we can use our first right-hand rule when we're dealing with a straight wire. And the first right-hand rule, if you look at it, you take your fingers and you curl them around the wire. Put your thumb in the direction of the current flow in the wire. Notice that if I do this right, curl my hand, I curl my hand around the bottom of the wire, wrap it around, imagine it going around behind my diagram here. Notice that my fingers come out at the top. So my fingers are coming out of the board on top. That's why we've got the dotted circles up here. And my fingers point into the board on the bottom. And so that's why I have my crossed circles, or sometimes I'll just use crosses. All right. B is magnetic field strength. And so when you see me right here, B field, that means magnetic field. Okay. Conventional current is the flow of positive charge in the wire. Okay. Now, let's say instead my wire is going into and out of the board. So it's going towards you on the screen, going into the board and going back here to my bookcase. And the current is flowing into the board at this point. All right. If I wrap my hand, my thumb is the current. So I point it into the board, and then my fingers would naturally wrap around in the direction. Okay. So you can see that this would create concentric rings. So notice that if I put my wire demo back up here, you'd see that if the current had been going down through the wire, wrap my hand around it, that would create rings like this around the wire. Okay? Now, what happens when we take 2 wires and put them next to each other? You create an interaction between each wire's magnetic field. And so that's what we've got here. This diagram represents that. On top here, we have 2 wires. They are adjacent to each other, and the current is flowing in the same direction in both of them. All right. Notice that with the top wire, it would, if we use our right hand rule, it's going in on the bottom of the wire, coming out on the top. And so that's why the symbols in blue are the way they are. The bottom wire, I'm using green to differentiate the symbols. But notice that on top of the bottom wire, it's going out. On the bottom of the bottom wire, it's going in, just like it is up here. But notice that that creates an opposed magnetic field in between the 2 wires. Well, an opposing magnetic field does what? Creates attraction. Okay, so these wires would physically actually come together. You can do this on a tabletop, and you would actually have wires rolling toward each other if you had current flowing in the same direction for both of them. Notice if you have current in the opposite direction, you create a magnetic field that is the same direction for both wires in between them. This would actually create a repulsion. Magnetic levitation, anyone? Okay. So here we have the interaction of current flowing in wires. Okay. Magnetic field strength around a straight wire. The magnetic field strength around a straight wire can be determined using this equation that Andre Marie Ampere, yes, the French mathematician whose name is given to the units of electric current, because this particular equation right here, he defined how strong the magnetic field was going to be based upon the current and how far away from the wire you are attempting to measure that current. Okay, so B, magnetic field intensity, mu0 represents the permeability of free space. Look on your reference table, it's there. Okay, I represents current and R represents the distance away from the wire. Notice that this is an inverse relationship between magnetic field strength and the distance you are away from a wire, but that makes sense anyway. The farther you are away from something creating the force is going to be less, okay? But notice it's not a squared relationship here, all right? That's because this is actually the circumference, 2 pi r, circumference of the magnetic field that's around the wire, okay? Now, what happens when we coil wire? We actually can create an increase in the strength of the wire around the coil, all right? So here we go. If you take a single loop coil, I hope you can see what I've drawn here. You got the loop going around and the current flowing that way in the loop. I can use my first right-hand rule here, all right? But it gets awkward when we're doing that, all right? But note that inside the coil, we have all the same direction for the magnetic field. Outside the coil, we have all the same direction for the magnetic field. So that means that inside, we have a uniform direction. Now, take this and loop it again, keep the current flowing the same way, and dun 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 dun, you've got the current of the next loop in the same direction as this loop. You've got the current in the following loop, same as the loop. Dun 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 dun, goes all the way down, and you create this situation right here. When you have multiple loops, all right, imagine this is a hollow tube, and I've got wire looped around and around and around and around and around it. Take this, imagine this multiple times down here, okay? So now we use the second right-hand rule. Notice I don't change my right hand, okay? But instead of the fingers being the direction of the magnetic field, the fingers now represent the coils of wire that are being looped, okay? And so for this one, notice that with current flowing in here and then going over and into the bottom, it goes around behind that and comes out through the top. And so we end up curling our hand in the direction of the current. The thumb this time is the magnetic field. So it's opposite of the first right-hand rule. First right-hand rule, straight wire, thumb is your current, fingers are the magnetic field around the wire. Second right-hand rule for a coil of wire, fingers are the current, thumb is the magnetic field inside the loop of wire. Okay, and now to wrap up, all right? Here we are. We've got a wire. And let's say that the current is flowing this way along the wire. Since it's a straight wire, I use my first right-hand rule, okay? And so I would take my hand, put my thumb in the direction of the current in the wire, wrap my hand around the wire, and that's going to be the direction of the magnetic field around the wire. Okay? Turn the wire towards you, and the current is coming towards you, out of the board, or out of the page, or out of the screen, if you will. Put your thumb in that direction, and your fingers will wrap around the wire. Okay? If we have the wire straight up and down, and the current is going up through the wire, put my thumb in the direction of the current, wrap my fingers around the wire. That means if I put a compass right here, it would point north that way. If I put the compass over here in front of the wire, it would point that way. If I come around, put the compass over here on this side, it would point toward me. I would suddenly be north of that compass. Turn the current off, it would then reorient itself to whatever the magnetic field is of that area. In this particular place, that's that way. All right. North is that way for me. Okay. All right. Take a coil of wire, and I just so happen to have one. Okay. So I've got a certain large battery here, and I've got a coil of wire. The wire has to be insulated. You can't have bare wire to do this. I've wrapped it around a drinking straw, and I am going to put this on here. And believe it or not, right now there's current flowing through the wire. Okay. Now, if I can get this to work right, all right, hopefully you can see this. Doesn't seem to be creating an interaction. Believe it or not, the current is happening. So if I take a ferromagnetic material and I add it to the coil, put it inside the coil, notice it's not electrically. Look at that. Okay. It's causing the compass to change its orientation. Therefore, one end of the compass is attracted, the other end is repelled by the magnetism that's created here. The current in the wire is inducing the iron in the nail to produce its own magnetism, and there we get a deflection. Hopefully you're seeing that in with the limited way I can use my laptop here to do this. Okay? You can always do this experiment on your own. Okay? If I change the amount of wire, let's say that instead of using a small amount of wire, I use twice as much to 3 times as much. And that's what I've done with this wire here. As you can see, there's a lot more wire on it. Okay? I should increase the field strength a little bit. And notice that, yeah, notice it's a lot stronger. Without even the nail, I'm producing a deflection in the compass. If I add the nail to it, notice that that deflection becomes even more powerful. Okay? Notice that over here I've got dun da da dun da da. I'm picking up pins with it. Disconnect it, and they all fall off. Okay? So there you have it. Electromagnetism. One, magnetism is a force that is an attraction or repulsion between charged particles that are moving. So if we force the motion with electric current, we create electromagnetism. The magnetism is mutually perpendicular to the direction of flow of the charge through the conducting material, usually a wire, okay? And in the case of electrons, we say our conventional current flow is opposite to their actual flow, all right? Negative charge goes one way, positive charge goes the other. We base everything on what old Ben Franklin and the old scientists thought of current always flows from high potential to low potential, which is from positive to negative. We now know that's actually opposite physically to what's going on in the wire here. Okay? Magnetic field strength. The amount of the magnetic field strength depends on the current flowing through the wire, I, and how far away you are from the wire. So if we measure the current out here, it's a certain distance from the wire. And using that equation, B equals mu 0 I divided by 2 pi r. 2 pi r because the magnetic field line goes all the way around the wire here. Okay? If we coil the wire and make a loop out of it, you then get an intensification of the magnetic field inside. The two right-hand rules we're using so far. Straight wire. First right-hand rule, thumb is the current, fingers wrap in the direction of the magnetic field around the wire. Make a loop of the wire. If the current is flowing in here, around here like this, then I would wrap my fingers in the direction of the current. Notice my thumb is pointing toward me. So that means the magnetic field is directed this way toward me through this loop. Okay? We'll be Zooming a teleconference to follow up this lesson. So please check out the worksheet that I've emailed you. Please check out the notes that are online on the website. And if you have any questions, we'll be doing it through the Zoom teleconference. Otherwise, you can email me. All right, that's heavyphysics at verizon.net. HEVYPHYZX at verizon.net, or use my school email address, AWELKLEY at brunswickcsd.org. brunswickcsd.org. Hope this lesson works for you for Unit 8, Lesson 2, and Intro to Electromagnetism. Bye-bye.